All right, let's talk about set operations. So we've talked about sets, we've talked about how to compare sets. What we're going to talk about in this lecture is how to combine sets, right? How to make new sets out of old ones. So we're going to talk about unions, intersections, set difference, and complements, okay? So let's get to it. The union of two sets A and B is denoted by A union B. So we call that symbol union. So we call this A union B. So U for union, right? A union B. And it's defined by X is in A union B if and only if X is in A or X is in B or both. Okay? So as long as X is in one of these sets, then we say X is in the union. You'll notice the striking similarity between this. Oh, I just realized I can make this a little bigger. You'll notice the striking similarity between this and the logical operator, the little V sign, right? And we said, P, V, Q is true as long as either P is true or Q is true or both. Right, so this is a very, very similar concept, right? Okay, the intersection of A and B is denoted by A intersect B. So we read this symbol intersect. So it's like an N symbol for intersect. So U for union, N for intersect, right? A intersect B. So A union B, A intersect B. And it's defined by X is in the intersection, right? X is in A intersect B, if and only if X is in A and X is in B. And once again, you notice the striking similarity between this and the logical operator, the little wedge shape, right? We would say, in logic, we would say P and Q is true if P is true and Q is true, right? And this is the same sort of thing, right? X is in A intersect B if X is in A and X is in B. All right. So, So in other words, A union B is the set of elements that are in A or B or both. So it's the combination of A and B. It's like you just take both of those sets and you put all of the elements that are in either one of them, you just put them into a set, right? And it makes sense to call this the union of A and B since we're uniting the elements of those sets, right? A intersect B is the set of elements that are in both A and B, right? So they have to be in both sets in order to be in the intersection. So it's made up of the elements that A and B have in common. It makes sense to call it the intersection because it's where they overlap, right? It's like the intersection of two streets, right? It's the place where those two streets overlap, right? Okay. And then, as I said a second ago, note the similarities in the notation. In logic, we have the little V, while in set theory, we have the little U. But both of these symbols relate to the notion of the inclusive or, right? In order to be in the union, you have to be in A or B or both. In order for the statement to be true, P has to be true or Q has to be true or both, right? And then again in logic, and I'm not sure why I have an extra E on the end of that, but in logic we have this little caret symbol, while in set theory we have this little intersection symbol. But both symbols relate to the notion of and. In order to be in A and B, you have to be in both A and you have to be in B, right? Or P and Q is true if both P is Q and Q is true, right? Here are some Venn diagrams, okay? So I'm giving you a whole bunch of different ways to think about this, so to hopefully make it easier. But here's some Venn diagrams, right? A union B would be the set of all. So this I'm thinking of like our universal set, right? This is our universal set. So A union B would be all of the elements in A or B or both, right? A intersect B is just the stuff that's in both A and B, okay? So let's practice. So A is the set 1, 3, 5, 7, 9. B is the set 1, 2, 3, 4, 5. let's find the union of A and B. So A union B. This is when we combine the two sets. All right? So 1 is in A, so 1 is in the union. 2 is in B, so 2 is in the union. 3 is in, well, 1 was in both. 3 is in both, so it's in the union. 4 is in B, so it's in the union. 5 is in both, so it's in the union. 7 is in A, so it's in the union. 9 is in A, so it's in the union. And that's what you would get, right? That's A union B. Now, A intersect B, on the other hand, this is only what they have in common, right? Well, they have a 1 in common, so 1 is in the intersection. They have a 3 in common, so 3 is in the intersection. They have a 5 in common, so 5 is in the intersection. 7 is in A, but it's not in B, so 7's not in the intersection. 9 is in A, but it's not in B, so 9 is not in the intersection. Okay, 2's in B, but not A. 4 is in B, but not A, so 2 and 4 are not in the intersection. So that's it as far as the intersection is concerned. It's 1, 3, and 5. Okay, so A intersect B is what they have in common. A union B is just combine both sets into one set. Here's some more. We've got A is 10, 11, B is 10, 12, and C is 12. Let's find A intersect B. A intersect B is what they have in common. So in this case, just 10. Part B asks for A intersect C. Well, A is 10 and 11 and C is 12. They don't have anything in common. So A intersect C would be empty, right? It's the empty set. Part C asks for A union empty set. Well, the empty set doesn't have anything in it. But we're talking about the union here. So we're combining A with, nothing, I guess. So that would just give you A, right? That would just give you 10 and 11. Or in other words, just A. So unions, you can kind of think of them like addition. And the empty set, you can kind of think like 0. So anything plus 0 is that same thing. So A union empty is just A. On the other hand, if we're looking at the intersection of A and the empty set, well, the intersection is what they have in common. And since the empty set doesn't have anything in it, then they have nothing in common, right? So you get A intersect empty is empty. So intersection, you can kind of think like multiplication. And again, empty set is 0. So anything times 0 is 0, right? A intersect empty is empty. Okay. Here's another example, because it doesn't just have to be numbers, right? So let's say that M is the set of all X, where X is a letter in the word mathematics. And let B be the set of all Y, where Y is a letter in the word beauty. Let's find M union B and M intersect B. Goodness. Well, letters in mathematics would be M, A, T, H, E. M we already listed. A we already listed. T we already listed. I, C, S. Okay, so those are all the letters in M. The letters in B, beauty. B, which we haven't listed yet, so we're going to put B in there. E, we've already listed. A, we've already listed. U, we have not listed yet. T, we've already listed. And Y, we haven't listed yet. Okay, so that would be A, M union B. All right, all of those letters. What about M intersect B? Now this time we're not just combining them. We're not just throwing them all together. We are trying to see what they have in common, right? So math has an M in it, but beauty doesn't. Math has an A in it, and so does beauty, so A is in the intersection. Math has a T in it, and so does beauty, so T is in the intersection. Mathematics has an H, but beauty doesn't. An E, and so does beauty. And M we've already done. A we've already done. T we've already done. I is in mathematics, but not beauty. C is in mathematics, but not beauty. And S is in mathematics, but not beauty. So They only have those three letters in common. A-T-E. Okay, so that's unions and intersections, right? Hopefully that makes some sense. The next thing we're going to talk about is complement. So if A is a subset of the universal set U, then the complement of A, denoted by A with a little apostrophe, we'll call it A complement, right? A complement is the set of elements of U that are not elements of A. So in other words, A complement, or I might sometimes call this A prime, but it's A complement is the set of all X where X is in the universal set, but it's not in A. You can kind of think of it like the opposite, right? But it's not quite the opposite. It's the complement, right? It's complement with an E, as in that which completes, right? Not complement with an I, as in an expression of praise, right? So you're talking about something that completes, right? So in other words, A complement completes A in the sense that when you take the union of A and its complement, you just get the universal set. So here's the Venn diagram, right? So if you've got a set A, and this rectangle represents, the universal set, which for the sake of clarity, I'm just going to point to it and say everything inside this rectangle is the universal set. A is here. A complement would be all of this stuff. It would be all the stuff that's not in A, right? All the stuff that's in the universal set, but not in A, right? This stuff would be A complement, right? That's A complement. So now if you think about A complement union A, that means you throw these things together. Well, then you're just going to get the universal set, right? You're just going to get the universal set. That's why we call it a complement, because it completes. A complement completes A. So let's see. It says find the complement of each set. In each case, the set U represents the universal set for that scenario. Okay, so for in part A, the universal set is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all the whole numbers between 1 and 10. And A is just the set of odd numbers, 1, 3, 5, 7, and 9. So A complement, I wrote an AC up here, right? But it should be A prime, A apostrophe. Right, A complement. This is another notation, A to the C power thing. That's another notation for complement, but anyway, A complement is the thing that completes A. In other words, it's all of the stuff in the universal set that's not in A. So what are we missing from A? What's missing here? Well, we're missing all the even numbers, right? We're missing 2, 4, 6, 8, and 10. So that's A complement. Okay, now it's important that A complement, this is relative to your universal set U. Otherwise, you would say, well, I don't know, what is A complement? It's like literally everything except for these numbers, right? But no, you have this universal set that tells you, that gives you your reference point. So it's all the stuff in the universal set that's missing from A, right? So A complement is all the stuff in the universal set that's missing from A. Okay, so let's look at another one. U is the set of people living in the United States, and I is the set of people who have photos on Instagram. Okay, so what's I complement? It would be the set of people living in the United States who don't have photos on Instagram. Right? So I complement is the set of people living in the United States who don't have photos on Instagram. Okay? So if this is seeming a lot to you like negation, right, like the logical operation of negation, then I think you're thinking of sort of the right idea. Okay? Okay, last one. U is the set of all C, where C is any card in a standard 52 card deck. And F is the set of all F, where F is a face card in a standard 52 card deck. So what is F complement? F complement would be the set of all, well, we already used C and we already used F, so maybe I'll call it X. The set of all X where X is a standard card, or it's a card in a standard deck, is, I butchered it, is a card in a standard, oh, I better start over. F complement is set of all X where X is a card in a standard deck that is not a face card. Now, if you don't know what all that means, then just Google it. Just Google, like, do an image search for standard deck of cards, and it'll show you all of the different cards, right? Face cards are jacks, kings, and queens. So, anyway, so this would include, like, ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? Anyway, I guess that's another way that you could say it. You could say, you know, it would be all of your aces, ones, so aces, ones, twos, threes, all the way up to tens, right? That would be the same set. Okay, very good. So that's complements. And then the last one we're going to talk about is set difference. Okay, so let's say that A and B are sets, right? The set difference of A and B is denoted by A minus B, and it's defined by A minus B is the set of all X, where X is an element of A, but it's not an element of B. Okay? So A minus B is the set of all elements in A that are not also elements of B. So it's basically like you remove any elements of B out of A, right? And that's why we think of it like A minus B. So here's a Venn diagram for that scenario. So let's say that you've got your universal set, and then you've got A and B. So A and B. A minus B would be all of the elements of A that are not elements of B. So it would be all of this stuff, right? But not the stuff in the intersection. It would just be that stuff. And you can kind of see that A minus B is the same thing as A minus A intersect B. You could kind of think of it like that. Anyway, but that's kind of interesting. Venn diagrams are nice tools to help us sort of wrap our brains around stuff. But okay, let's practice. It says, find the difference between 3, 6, 9, 12, 15, 18, and the set of all X where X is an odd integer. So we want to take this set and remove any elements that are in this set. So we want to remove any odd integers out of this set, right? So removing any of the odd integers. Well, 3 is an odd integer, so it's got to go. 6 is even, so it can stay. 9 is odd, so it's got to go. 12 is even, so it can stay. 15 is odd, it goes. 18 is even, it stays, right? So there's that set difference. Okay, here's another one. We've got E is the set RBET and L is the set YET. Let's find E minus L and L minus E. E minus L is going to be all of the elements in E, but we have to kick out any of the elements that are in L. So it's going to be, well, let's see. R is in E, but it's not in L, so R can stay. B is in E, and it's not in L, so B can stay. E is in E, but it's also an L, so we've got to kick it out. T is in E, but it's also an L, so we've got to kick it out. So E minus L is just RB. What about L minus E? Well, L minus E. Y is in L, and it's not in E, so Y can be in the difference. E is in L, but E is in E, so we got to kick it out. T is in L, T is also in E, so we have to kick it out. So L minus E only contains the element Y. And you can see right away that E minus L and L minus E are not the same thing, right? They're not the same thing. Okay, so that's set difference. Now, what I want to talk about for the rest of this section is how do all of these things combine together? Like in what order do you do like intersections, complements, set difference? Like what order do you do these things in? So what I want to suggest to you is that you do these things in order from left to right, unless there are parentheses. If there are parentheses, then you do the stuff inside of the parentheses first. Okay? And that's all there is to it. Though that's like the order of operations for sets. You work them out from left to right. If there are parentheses, do what's in the parentheses first. So for example, let's say that we have this scenario, A intersect B union C. Now, because B union C is in parentheses, I'm going to do B union C first. So I'm going to rewrite this. First of all, let me rewrite A is the set 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I'm going to intersect that with whatever B union C is. So I've just rewritten A there. B union C is going to go here. So what's B union C? I'm going to take B and I'm going to take C and I'm going to put them together, right? I'm going to marry them. So 2 will be in there, 3 will be in there, 4 is in there, 6 is in there, 8, 9, 10, and 12, right? That's B union C. And now I have to take the intersection of these two sets, okay? So I did the stuff in the parentheses first. This one just came along for the ride. And now I'm going to take the intersection of these two. So the intersection is going to be whatever they have in common. In this case, they've got a 2 in common. They've got a 3, a 4, not a 5, but a 6, not a 7. They've got 8 in common, and they've got 9 in common. And that's that. Okay. Now part B, on the other hand, here there are no parentheses. There are no parentheses, so we're just going to work this out from left to right. Or if you can do it all at the same time, even better, because we're just taking intersections. So we're doing A intersect B intersect C. A intersect B intersect C. So it would be the stuff in this set is going to be what all three sets have in common. So 1 is not going to be in there because 1 is in A but it's not in the other two. 2 is not going to be in there. 2 is in A and B but it's not in C. 3 won't be in there. 3 is in A and C but it's not in B. 4 won't be in there because it's not in C. 5 won't be in there because it's not in B or C. 6 will be in there, right? 6 is in A, 6 is in B, 6 is in C. So 6 is in the intersection of those three sets. 7's not in there, 8's not in there, 9's not in there. So only 6 is in here. Only 6 is in the intersection. Now, if that's too much for you, then like I said, you could do it one step at a time. You could start off by doing A intersect B and write down A intersect B is going to be 2, 4, 6, and 8. And then you do that intersected with C. So you do 2, not in here. 4 not in here, 6 is in here, and 8 not in here. And so you would just get 6, right? So you could do it one piece at a time, one step at a time, and that would be fine. Or you can do it all at once. Okay? Here's another example. We have A union B minus A union C. All right, so I'm going to do the stuff inside of the parentheses first. A union B. A union B. So that's going to be 1, 2. Well, it's going to be everything from 1 to 9, and then also 10. So it's going to be 1 to 10. And then I have to do set difference with A union C. A union C, let's see, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 12. Okay. Okay, that's interesting. So now the set difference. The difference of this set and this set is it's everything in this set that's not also in this set. So if there's anything here, we have to kick it out from the set difference. So for example, 1 is in this set, but it's also in this set, so we kick it out. 2 is in this set, but it's also in this set, so we kick it out. Same thing with 3, 4, 5, 6, 7, 8, 9. The only thing that's going to end up here is 10, because 10 is in A, or 10 is in this first set, but it's not in the second set. So 10 is the answer there. Okay, and again, I did this here, I did this here, and then I took their difference, right? So I did the stuff in parentheses first, and then I did the set difference. Okay. Now here's an even more complicated one. So it says, let U be the universal set. U is the numbers from 1 to 10. Let E be the set of all x where x is even. Let B be the set 1, 3, 4, 5, and 8. And let A be the set 1, 2, 4, 7, and 8. Let's find A union B complement intersect E complement union A. Whew. All right. So first things first, right? In order to do A union B complement, I need to know what A union B is. So let's do A union B. And besides, that's inside of parentheses, so I need to do that first anyway. So we need to do A union B. Right, so A union B is 1, 2, 3, 4, 5, 7, and 8, right? So it's the combination. We're combining those two sets. So there's A union B. So then that means, right, that A union B complement, A union B complement is going to be all the stuff in the universal set that's not in A union B. So 1, 2, 3, 4, 5, 6. We're missing 6. 7 and 8. We're missing 9. And we're missing 10. So there's A union B complement. Okay, so that takes care of that. Now, I want to intersect that with E complement union A. So I need to figure out what E complement union A is. Well, in order to figure out what E complement union A is, first I need to figure out what E complement is, right? So what's E complement? E is the set of all even numbers. So E complement would be the set of all odd numbers, right? You could list them off, 1, 3, 5, 7, 9, okay? But that's E. That's E complement, rather. Okay. So if E complement is the set of all odd numbers, then E complement union A is going to be Well, A is 1, 2, 4, 7, and 8, and E is all of the odd numbers. So we're going to get 1, 2, 3, 4, 5, 7, 8, and 9. Okay, so I put all the odd numbers within the universal set, 1, 3, 5, 7, and 9, and I put all of the numbers in A, 1, 2, 4, 7, and 8. So we've got them all in the union there. Now I want to take the intersection of those two sets, right? So A union B complement intersect E complement union A is 6, 9, 10 intersect 1, 2, 3, 4, 5, 7, 8, and 9. Now the intersection is what they have in common. So what do they have in common? Well, they don't have a 6 in common. 6 is not in here. They do have a 9 in common. And they don't have a 10 in common. 10's not in here. So it'll just be 9. Okay? Okay, so that's that. Here's another example, and this one will lead us to an interesting fact, okay? But let's say the universal set is 1, 2, 3, 4, 5. Let's say that A is 1, 3, 5, and let's say that B is 1, 2, 3. Let's find A union B complement. Well, in order to find A union B complement, first we need to find A union B. So A union B is going to be 1, 1, 2, 3, and then 5. Okay? So if that's A union B, then A union B complement would be all of the stuff in the universal set that we're missing from A union B. So what are we missing here? We're missing a 4, it looks like. We're missing a 4. So A union B complement is just 4. Okay? All right. Well, so now let's look at A complement union B complement. In order to figure out what A complement union B complement is, first we need to figure out what A complement is. So A complement. A is 1, 3, 5. So what are we missing here? We're missing 2 and 4. B complement, what are we missing here? We're missing 4 and 5. Okay, so then A complement union B complement would be 2, 4, and 5, right? It's the union, so it's the marriage. We're throwing them all together into one set. 2, 4, and 5. So there's A complement union B complement. All right, so this example shows us that A union B complement is not the same thing as A complement union B complement. You can't just distribute the complement and get the same thing. But if you squinted it just right, notice that if we had changed this to an intersection instead, right? Note that A complement intersect B complement here. It's what they have in common, and that would just be 4. Well, that is the same thing as A union B complement. So A union B complement is A complement intersect B complement. That's a fact known as De Morgan's laws. We talked about De Morgan's laws for logic when we were talking about logic. Well, it turns out that we have similar laws for set theory, right? So if A and B are sets, then A union B complement is A complement intersect B complement, just like we saw in the previous example. A intersect B complement is A complement union B complement. So you change from union to intersection when you distribute the complement, right? You change from intersection to union. And it's very, very similar to De Morgan's laws for logic, right? We said not P or Q is logically equivalent to not P and not Q. Whereas not P and Q is logically equivalent to not P or not Q. But it's the same thing. You switch from or to and whenever you distribute the negation. You switch from and to or when you distribute the negation. So it's the same thing, right? Very, very similar. Okay. Last thing I want to do is just do a little bit more practice with Venn diagrams. So let's see if we can draw a Venn diagram for each of the following. So we want to do A intersect B minus C. Ooh, so we're going to have 3 bubbles this time. And we need to make sure that they all overlap in all of the different possible ways. So I'll show you what I mean by that. But A intersect B minus C. I might use a pencil for this one because I feel like I might make a mistake that I'm going to want to erase. But let's give ourselves a universal set. And then I'm going to put A up here. So this is our universal set, by the way. I'm going to put A there. And then I'll put B here. And then I'll put C here. Okay. And you'll notice, so I've got A, B, and C. You'll notice that I've got a little place where B and C overlap, but A doesn't. I've got a place where A and B overlap, but C doesn't. I've got a place where A and C overlap, but B doesn't. And then I've got a place here where all 3 of them overlap. And then in the remaining regions, right, this is just B. This is just C. This is just A. And then this stuff is like none of them, right? It's like the 3 things, it's the complement of the 3. Okay. We're supposed to find A intersect B minus C. Well, in order to do that, let's first shade in what B minus C would look like. So B minus C would be all of B except for the C region, right? So it would be all of this stuff, right? So that would be B minus C. Now we want to take the intersection of that with A. So that would be what B minus C has in common with A. So that would just be this stuff, right? So my final answer is this. Right? A, B, C, and it's just this region. Right? So it's just this region. Okay, so there's my Venn diagram. That's my final answer. Okay, let's do another one. Oh, so we've got A intersect, B intersect C, complement. Okay, so same deal. We'll need 3 circles to represent this scenario. I'm going to do a rough draft in pencil again in case I need to erase. But I'm going to have A, B, and C, like that. Okay. I need to start on the inside, on the innermost part. B intersect C. So B intersect C would be this stuff here. And then I want to intersect that with A. Well, that would just be this stuff here. Okay? And then I want to take the complement of that. So actually it would be everything else, everything except for this part. Right? So it would be everything else, everything that's not that part. So my final answer is going to look like this. Okay, it's going to be this entire rectangle, right? Except for that little tiny portion in the middle. So it's all of this. Right? So it's everything except for this. It's everything else. That would be my Venn diagram. Okay? And then we can go the other way. We can describe the shaded region using set notation. So, for example, here, goodness, what would this be? It looks like the stuff that, it's kind of hard to tell, right? But it looks like the stuff that's shaded in is A and B, except for the middle part. So I would call this A intersect B, or sorry, A union B minus the intersection, right? So it would be A union B. A union B would give you the whole thing, but we're missing the intersection. So we say minus A intersect B. Okay? What about part B? Man, when you get 3 circles in there, it starts to get really, really confusing. But let's see. What do we have shaded in here? So we've got this region, and this region. So what would that be? Well, this region looks like A intersect B. This region looks like A intersect C. And then it looks like we're combining those two. So I would do a union. I would say A intersect B union A intersect C for that one. Now, is there more than one correct answer? Yeah, potentially, right? Not all of them are going to have more than one correct answer, but some of them might. So there might be another way to describe this. I mean, one thing that you could do, for example, is you could describe everything else. You could describe everything that's not shaded, and then just put the little complement sign on it, and then boom, you've got these, right? So there's going to be at least 2 ways to describe each of these sets. But these are the ways that occurred to me. If you thought of another way, let me know, and I'll let you know if it's correct. Okay, but that's that. That's all I wanted to say about combining sets.